All right, another option that we could do in physics, IB, is imaging. And imaging is all about optics, how light behaves through lenses, prisms, mirrors, how we can use imaging for medical field stuff, how our eyes work, things like that. So for this first topic, we're going to talk about ray diagrams and some general imaging equations, like an introduction to imaging. So let's start by talking about imaging ray diagrams. We're going to talk about two different scenarios, mirrors and lenses. Mirrors primarily reflect light. So when light hits it, it bounces off 99% of the light and reflects it back to our eyes. Lenses, light passes through it and refracts it. So it doesn't mean that reflection and refraction don't happen with the other cases, but that's primarily what happens. What we're going to focus on are curved mirrors and curved lenses. So not prisms or flat mirrors. And for curved mirrors and curved lenses, what happens is that they have a focal point, which means when light hits it, it either reflects back through a point or it refracts through a point. And the focal point is used to help figure out what do we see when we use that lens or mirror. So in order to figure out what the image looks like when we observe these things, we usually have to draw a ray diagram. And the way you draw a ray diagram is you can draw multiple rays of light traveling through the lens or hitting the mirror. And where those rays cross, that's where we see the image. Now actually, to make it simple, we can just simplify this as two rays. Two rays. One ray we can draw is from the focal point to parallel, because when something hits a focal point, like for a mirror, if I have a light coming through this focal point here, it's going to hit this, it's going to reflect back at the same angle, it's going to go back parallel. The second ray I can do is starting from parallel, if I go this way, it's going to reflect to the focal point, opposite direction. So I could draw any rays I want, I could draw one down here, parallel, and it's going to go through the focal point too. Boom. So we're going to simplify this process. We're going to draw an object and take a point on that object and draw those two rays, and we'll see how it works. Let's show you right now. Let's look at case number one, a concave mirror. What does a concave mirror mean? It means that when we draw a line here, this line is like the middle point where we're going to reference everything, like the equilibrium point. This is also called the principal axis. I'll label that principal axis. Principal axis. And here's my mirror. So this is the shiny side of the mirror on the left, and the back side of the mirror is the part that's not shiny. So here's an example. This is a mirror, and it's curved, and this is the back side. This is what we're getting at right here. I'm just drawing that. And then I'm going to draw an object. For an object, I'm just going to draw an arrow. That's usually pretty common. Just draw an arrow. And the arrow's pointing up right now. So whatever it is, it's standing up on the principal axis. And then the mirror has a focal point somewhere in here, usually labeled F. Now the distance from the focal point to the mirror is called the focal length, which we'll talk about later. And the distance from the object to the mirror is called the object distance, which makes sense. So we're going to use this ray diagram, these two rules, these two rays to draw a ray diagram. Where do we see this image? So first one, I'm going to draw a point. Let's look at the top of the arrow from the focal point to parallel. So if I have a ray, it's going to go of light. It's going to go through the focal point, hit this mirror, and then it's going to reflect back at the same angle. Angle of incidence equals angle of reflection. It's going to reflect back parallel. Parallel means parallel to the principal axis. That's why we drew that line. The second ray we can draw is, let's draw a ray that's parallel to the principal axis. And it's going to hit this mirror. It's going to reflect to the focal point. And look at that. Those two lines cross right there. So that's where the tip of my arrow would be. Is the tip of my arrow? Hello? Is the tip of my arrow? So my arrow is below the principal axis, so it tells me that it's upside down. So when I use this mirror, here's what if I'm far away from a curved mirror like this, What does my image look like? Well, I can say a couple things about this image. One thing I can say is it's upside down. We say that the image is inverted. Inverted means upside down. Second thing I can say about this image is it's real. And we'll talk about the difference between real and virtual. A real image is something that you can actually project on a screen. So if I take this mirror, I can actually use it and put a screen right here, or a piece of paper, or some sort of object here, and I can actually see the light hit that screen, or object, or piece of paper, and it actually shines light on that object, and I can see it on that object. It's a real image. So this is inverted, and it's real. Now, the size of this, right now it's relatively the same size. There's actually an equation we can use to calculate the size of it. We'll get to that in a bit. But based on looking at it, it looks like it's pretty close to the same size. It's just flipped upside down. But that can be dependent on the distance away. The distance away can change the size. Like I said, we'll calculate that in a bit. Now, the second case we're going to look at is, what if you're really close to the concave mirror, like inside the focal point? What happens then? Well, we're going to use the same two rays to draw a ray diagram. So first we're going to, I'm actually going to do the second one first because it's a little easier. So first I'm going to draw a line parallel to the principal axis. It's going to hit the mirror. It's going to reflect through the focal point. Then I'm going to draw through the focal point to parallel. Okay, I'll do that in blue. So it means I got to start at the focal point. It's got to hit the tip of the arrow, and then it goes parallel. So light starts basically from the tip of the arrow, and it appears like it comes from the focal point, hits this, and goes right parallel. Now, where those rays cross, the blue ray and the red ray, where those rays cross, that's where you see the image. But they don't cross. I could keep drawing those lines, and they get farther and farther apart the more distance I cover. So what I do is I follow the rays back behind the mirror. So I'll do that with like a dotted line. A lot of times if you have to extend or extrapolate the rays, you do that with a dotted line. So I can extend that one forever. I can extend this one forever. And right there is where it crosses. That's where the tip of the arrow would be. And since it's above the principal axis, I know it's right side up. So with this image, I see a couple things. One, I see it's larger. There's no place, even if I move this, it just makes this larger and larger. So first, this is say a magnified image. It's a larger image. Now we can actually calculate this once again with the equation, which we'll get to in a bit. But we know for sure it's magnified. What else can we say? Is it upside down? No, it's right side up. We say it's upright. So upright or inverted. The last thing we could say, is this a real image? Could I physically put a piece of paper behind here and actually see an image? And the answer is no, because the light hits this mirror and it's going this way. There's no light that can actually get to the mirror or to the piece of paper behind the mirror. So it's an optical illusion. We look at this mirror, we see something behind the mirror, but there's nothing there. There's nothing physically behind that mirror. So we call that a virtual image. It's in a virtual world. Meaning, like, we don't see it. It's an optical illusion. Our eyes are playing tricks on us because we think it's coming from behind the mirror, but in reality it's hitting the mirror and bouncing back to our eyes, so it appears like it's coming from behind the mirror. So this is a virtual image because it's behind the mirror. No light is actually getting there. And that's kind of represented with the dotted lines. So we can actually say three things about this image: magnified, upright, and virtual. Now, what does that look like in real life? Well, here's a mirror. It's curved, as you can see. Right now, we can see that in the first case, we saw that it was a real image, and it was upside down. So if you look at this, I'm looking at you're seeing the back of the room right now, and all the lights are on the bottom. Now, when I move close, if I move inside that focal point, something weird happens. It gets kind of weird and blurry and shifty, and at some point, you start to see, oh my gosh, there's the computer screen. There's you guys. And it's right side up, and it's bigger. It magnifies it. And then you see a picture inside a picture because it's reflecting off the same mirror multiple times. So it goes on for infinity. So that's why it works. At some point when it gets blurry, it's kind of transitioning from going real and upside down to virtual and right side up. So it's kind of weird when it goes to that middle point. All right, look, I changed my shirt. So the next one we're going to do is lenses. We're going to get away from mirrors and talk about lenses. Lenses, like I said, mostly refract. So the light doesn't bounce back off of them, it travels through, it bends it. So first case we're going to look at for lenses is a converging lens. Converging lenses are ones that take the light and bends towards, like it doesn't bend out, it bends towards a point. And in order to have a converging lens, you have to be thicker in the middle of the lens and thinner on the outside. Now, it doesn't necessarily have to look like this. You can have lenses that look like this, or something. It's a terrible picture, by the way. Like some glasses will do this, where they, this is probably a better picture, but they're just thicker in the middle. And other glasses would be skinnier in the middle, where they do something like this. And that's a diverging lens, where the light spreads out when it goes through. So the first case we're going to look at is a converging lens. And what we'll do is we'll draw the ray diagram. I'll use a blue marker here. And we're going to use the same two rays to figure out what happens. So the first one we're going to do is we're going to draw a line through the focal point. Then when it hits the lens, it's going to go parallel. So here's our arrow we're referencing. We're going to draw a ray through the focal point, and then when it hits this lens, it actually does refract like this a little bit, and it refracts again parallel. It goes through. It's parallel to the principal axis. We could just simplify that and just talk about it hits the lens and goes parallel. It's a shortcut. The other one we're going to draw is through, it's going to start parallel, and then refracts down a little bit, and refracts down a little bit more through the focal point. And look at that, they cross right there. So I could have abbreviated that or shortened it just with like parallel and then went right to the focal point. That's eliminating the ray inside the lens. It's just a shortcut. So, where do they cross? The tip of the arrow crosses right there below the principal axis, so we know that the arrow is inverted. So the arrow is, well, it's inverted, it's upside down. And the size of the arrow, it can depend. Right now it's roughly the same size, maybe a little bit larger, but that depends on the distance. And the equation we're going to talk about later is going to go over what the magnification is. But for sure it's inverted, and it's real, because I could take, because it's actually light that is hitting this point, I could take some sort of detector, like a screen or something, put it right here, light's going to hit that screen and produce an image upside down. This is exactly how projectors work. You take light from inside the projector, shine it through the lens, and it projects it upside down. So what we have to do beforehand is flip it upside down, so that when it projects it, it flips it right side up. A second solution to that is just to put it through two lenses, put it through one that flips it upside down, and then put it through a second lens which flips it back side up. But it depends on the situation that we need. So it is real. It's a real image. So here's an example of a lens, what it could be. It's a pretty big one. It can possibly show a real image here on my arm with the, there you go. See how that light gets on my arm? That's coming from this ceiling up there. There's light that hits my arm. That's the light from the window or the ceiling lights hitting my arm, and it is upside down. It's actually the window. The window is upside down. You can barely see it, but it does flip the image. And it's smaller based on the distance because the window's really far away and my arm's really close. So if that's the case, it becomes smaller. If I move the opposite direction, move really far away, it gets bigger and bigger. So now the next case we're going to talk about is using the same lens that we talked about, the converging lens, one where it's thicker in the middle. But now we're taking the object and moving it really, really close to that lens. And what ends up happening is when we're inside the focal point, instead of flipping the image, it actually magnifies the image. And we're going to talk about why that is with this ray diagram here. So it's using the same lens, but now we're putting the object really close to the lens, just like it would do with the concave mirror. So let's use our ray diagrams to figure out what the image looks like. First line, let's do it in code this again too. So focal point to parallel. Let's actually do the other one first. Parallel to focal point. So first I'm going to go parallel. Once again, it does refract here, but I'm just going to draw a line to like the middle-ish area, and then to the focal point. So the same ray as the other one, it doesn't change. But now the second one, maybe I'll do this in green. I want to start from the focal point over here. It's going to go up to this lens. It does refract a little bit, but that eventually does go parallel. And look at that. This and this never cross. The farther away I get, the more they diverge. So what we do is we trace it backwards. We trace this ray back. So extrapolate to the, a lot of times this is on the dotted line again. And then we trace this ray back with the dotted line. And then cross right there. We'll draw that image in red. It's up, right side up because it's above the principal axis. And it's really close to the other one. The image appears almost on top of the object, but it is larger. So what kind of object is it? Well, obviously, it is an upright image. It's upright because it's above the principal axis. It's magnified. Hence the term magnifying glass. It's always going to be magnified or larger than the object. And also, it's a virtual image because if I put light, or it's not light, if I put a screen right here, it doesn't actually produce any image on there. This is like optical illusion. The light's actually over here, but it's an optical illusion that we think the light's coming from back there because of where the focal points are acting. So we can't actually put anything over here to get a real image. Nothing can be produced. It's light that's virtual because it's on our side of the lens. It doesn't actually exist there. We're just seeing it there because of the way the lens refracts light. So it is virtual. Just like how like with behind the mirror, it's virtual. In front of a lens, it's virtual. That's another way to remember it. Okay. Now let's look at what that looks like with this lens. I'm going to move this really close to the computer and see what that looks like. See if you can see the words on the wall here. See what it looks like with the words on the wall. And at some point they get, it's blurry. I'm not able to get it. But the images are getting bigger and it's kind of fuzzy. I just can't get it in focus right now. So it did magnify them and it didn't flip them around. It said virtual and inverted and you could see it right side up and nothing was flipped around, so that's good. Alright, next case number 5, is a diverging lens. Diverging lenses happen when they're thinner in the middle than they are on the outside, which means when light hits it, it actually doesn't bend in, it refracts outwards. So it diverges the light instead of converging to a point. So let's do our ray diagram to figure out what this image looks like. We'll go parallel to focal point again first. So parallel. But now it doesn't go through this focal point because it diverges. It goes out this way. So the direction that it diverges actually appears like it goes through this focal point. It almost looks like it comes from here. So it diverges in this direction when it hits this. Because it hits here, bends up, and then it hits here and bends up again. So that is diverging. The second ray we can do is going to the focal point. But let's head to this focal point over here. Because once we hit one focal point, we got to hit the other one too. Just like with the other lens. We're heading towards that focal point. Like we're going to cross it. But it doesn't actually cross it. It bends up a little bit and then bends up a little bit to parallel here. So those two rays will never meet up. They diverge. So what we do is we trace them back. I trace this ray back in green. Trace this one back in green. Otherwise a dotted line works fine too. They cross right here. That's the tip of the arrow above the principal axis. And what do we see? Well, a couple things with this image. Actually, you just know 3 things for sure. One, it's upright. It's above the principal axis, it's the same direction. It is upright. Also, it's shrunk. It's always going to be, the image is always going to be tinier than the object, so it's smaller. And it's virtual because no actual light is hitting that spot. The light is over here. It's in front of the lens, so it's a virtual image. So here's a lens that does that. It's kind of small. It's a diverging lens. No matter where you place this, the ray diagram is always going to be the same. Even if we put it inside the focal point, it's going to be the same ray diagram. It's always going to make it upright, smaller, and virtual. So look at what my eye does here. Little bitty eye, little bitty eye. It's actually kind of funny when I take the magnifying glass on one eye and the diverging lens on our eye. Let me do that real quick. Okay, so this is the diverging lens. Little bitty eye. Here's the magnifying glass. Big eye. What? What? Whoa! All right. All right. The last case we're going to look at is like a microscope or telescope. Basically, something where you look through one lens and you actually have two lenses, or a lens and a mirror put together. And what ends up happening is that light does, every time it hits a new lens or a mirror, it does a reflection or refraction again. So it just keeps going. So a microscope actually uses two lenses. It uses an objective lens and an eyepiece. So let's say that arrow over there is like, here's my eye, I'm looking at a microscope, and I look through the eyepiece, and so that does something, and then that light goes through the objective lens, and that does something, and I see that that arrow there. And it can be something really small, but the arrow should be magnified. That's the goal, is you want to make that small thing magnified. And the cool thing about microscopes and telescopes and other different types of equipment is that you can actually change these distances and actually change the lenses too. You can actually rotate what lens you use and change the distances to get it in focus and get it enlarged and all these different things. It's a cool thing because it's just playing around with the distances and the fractions of the lenses to get it clear and enlarged because you can see small things. Even stars out in the sky, they appear small, so you want to enlarge them to see what they look like. So what we do is we do it in two steps. We draw two ray diagrams, essentially, but in one picture. So let's just ignore this eyepiece over here, pretend it doesn't exist, and just draw the ray diagram for this lens. It's a converging lens. Objective lens is a converging lens. So we're going to do the converging lens ray diagram. So it goes parallel to the focal point. Then it goes focal point to parallel. And bada bing, bada boom. It's not perfect, but my ray diagram looks like this. It's upside down and real. Then what we do next is now we ignore this lens. And we treat that, because it projects real light right there, that real light then travels through the second lens. And so basically the rule of thumb is the image produced by the first lens becomes the object of the second lens. Now we just like ignore this, pretend this is a real object because the lenses don't know if it's a real thing, like if it's an object or if it's just a reflection of an object, or if it's a real image, it sees it as the same thing. So now we'll do this in green. Oh, we're inside now, so this is acting like a magnifying glass. So we're going to draw a parallel to the focal point. And then remember, since we're inside the focal point here, this second lens, we go, wow, so there, the parallel, and they never meet up. So we trace it backwards. We trace this right back, and this right back, and there is the tip of our arrow, what we see. So we look at, through these eyepieces, like here's our eye, here's the microscope. We're looking at this object here, and we see this image. It is bigger. It is bigger. Is it real or virtual? Well, it started off as real, but we're not seeing the real part, we're seeing the virtual part. We see the ending goal. So we see a virtual image, and it's enlarged. So virtual, enlarged, or magnified, and it is inverted. So when you look through a telescope or microscope, everything you see is actually upside down, but a lot of times it doesn't matter. Like, what are you looking at? You're looking at a cell? Well, who cares if it's upside down when you look at it? You get the same details. Well, I can see the mitochondria, or I can see the nucleus, or whatever it is. It's upside down, right side up, whatever it is. I look at a star. Does it really matter if it's upside down, right side up? So those are the different ray diagrams. If you can draw those, you can draw any ray diagram here. And the next video we'll talk about the equations that we can use to actually calculate magnification and focal lengths and where the object and images are. You kind of check your work, but the ray diagrams are a visual to show you what are you actually seeing. And the differences to note, so it's upright or inverted. Is it real or virtual? And then finally, is it magnified or shrunk? That one is, you can kind of get, if you're a good drawer, from the Venn diagram, but the calculations will verify those three things for you as well. So next video, I'll go through those and hopefully you learn something and it makes sense. So take care.